All right, welcome. Here is the plan for the week. We are going to be finishing Unit 8 this week, and we'll have a test of some sort. No, I think I want to try to potentially save a day, meaning like I'll open up a test and just kind of let it linger and sit there for a while.
Oh, I like that. I didn't say that.
So, yeah.
Oh, like open it Thursday and
Yeah.
leave it open till Friday night
Yeah.
or something like that.
Something like that.
That's
Because that'll save us a day, and I think that extra day sounds pretty nice for review.
yeah.
Um,
And I hate tests on Monday.
Wait, this.
I do too.
Everybody does.
Yes. We have, okay, so let me, yeah, you're gonna get some time on number 2 today. Okay, so, and number 2 is short. 8.8, we're gonna finish today, 8.9 tomorrow, 8.10 Wednesday. Thursday, we'll have an in-class review, kind of a catch-up, homework, everything kind of day on Unit 8. And then I'll open up the exam, and I'll kind of just let it sit there, and you guys can take it when you can take it. That way, it saves us a day. And again, since it's all online anyway, maybe I should have been doing that all year. I don't know. Oh,
Too late now.
I know. But what we'll do is then we'll start Unit 9. Unit 9 will be quick. Again, there's 10 topics in Unit 9, but I can't imagine us taking more than like 8 days of class to cover it. So we'll have a good, hopefully, week and a half-ish of full-on review. We are under 4 weeks away from the AP Chemistry test. If you are not currently spending a half hour a day studying for AP Chemistry, I would consider changing that behavior this week. I have sent you the link for a bunch of free response. I have a multiple choice test that I passed out last week. If you didn't get that packet of the multiple choice test, they are downstairs in the main hallway there where all the pickup supply stuff is. I didn't bring any with me today. I probably should have. Sorry about that. But if you go to the first floor, you're not?
Maybe. No, he's not.
Anyway, if you need that multiple choice packet, it is downstairs on the first floor of Wausau West High School. You're more than welcome to come grab it. My plan is to give you another multiple choice packet this week, and another one the week after, and another one the week after. So you should have good 4 or 5 multiple choice tests, a good 4 or 5 free response tests that you can look over and check, answer keys, and all the whole 9 yards.
Wait, is the answer key up?
I haven't put it out yet. I was considering doing that today. Did you finish it?
Well, I'll finish it tonight.
Oh, so why are you complaining about the answer?
Well, I'll need it tonight.
Oh, okay,
So it
okay.
just means
I see.
it'll be open.
My bad. All right.
Alright.
Yes.
Hypothetically, if someone didn't sign up for this test this year, I'm asking for a friend, of course.
Yeah. Okay.
Could
Yeah.
you sign up for that like next year and just like kind of remember it? And do
Yay.
like 30 minutes now, just do that for a whole year.
You'll still sign up right now.
No.
Or is it too late?
There's like a couple months.
I mean, maybe you still can. I don't know. AP might they like money, so they
Well, I
probably
know
charge
there's
like
like-
twice as
I
much.
know there's a late fee sign up you could do.
Yeah,
I thought that might have
I-
been back in like February.
Yeah, that might be closed. I'm pretty confident that's closed, but I don't know. AP likes money, so maybe it's still take it. Anyway, so to answer Logan's question of whether that's a good idea,
I mean, yeah, not
No,
a good
that'd be a
idea.
bad idea. A year without.
the test, the test is not easy when you're in this class.
Something out of for a year.
The test is more not easy when you're not in this class. Yeah, it would be extremely difficult. There was a student from last year's group who didn't pass last spring, who was emailing me and thinking about trying to potentially take it again this year. And then they're like, no, I didn't shut it down. I said, yeah, that's cool. I'll help you. You can even sit in class if you want. Here's a whole bunch of stuff. And then they're like, I'm good. Never mind. So, yeah, I think not being in the class and trying to take that test would be extremely difficult. It'd be extremely difficult.
If you took it, would you get like live on it?
Yes, yes, I would.
Would you get 100%?
I would probably not get 100%, but I would probably be in like the 98%.
Wait, isn't a 5A?
Sure, give me one. I still haven't taken the 2019 one. I'll take it.
You just take it for
Kind of.
That's
Is it not fun?
well,
Not fun for
Wait,
your
I
maybe
thought
for
it
you,
was
but-
100%.
What's that?
I thought a 5 was 100%.
Oh, gosh, no. No, a 5's like 75%.
Well, it's all based off of how the entire nation does. So like if the entire nation, like the best scores are like 40%, then that would be the 5. And
Historically speaking,
So collectively, we all.
that's
we
how
talked
we
about
got
this discussion before.
there's hundreds of thousands of students who take it, so good luck with that.
All I need is, I can get it.
Yeah, and I'm sure if you wouldn't be able to find that Reddit.
Brian Brett type.
Didn't they try to bait people?
Yeah, they set up such a like.
So,
It worked too.
to pass the AP chemistry test, you need roughly a 55% on the exam. That sounds really doable. It's really tough. If you finish that multiple choice packet I gave you last week, there's 50 questions on there. Yeah, you need to get 55% on that thing. And that's the easy part of the test, because I think the free response portion is harder. So keep that in mind. I mean, it's your first crack at it. If you are doing that multiple choice test and you get your result and you got like a 50%, it's like, don't be too discouraged. That's your first try, right? We'll have more attempts, and I think you'll get better each and every time you try it.
So, the multiple choice.
Yeah. It's got to, I mean, I maybe some people would disagree with me, but the multiple choice, because you got 25% chance inherently just with the number of options, right?
Yep.
In the free response question, you have inherently 0% of anything.
Yeah.
Jacob?
Well, once the test is the multiple choice one.
They're equally split, 50-50. So the multiple choice and the free response are equally weighted 50% of your total score.
How long is the test?
You have an hour and a half on 60 multiple choice questions. You have an hour and 45 minutes on 7 free response questions.
Why don't we get that much time for our test?
Because my test is not that long. Yours is way longer. All right, I sense a little more fear. I sense a little more fear this week than there was last week. That's a good
I
thing.
think everybody started.
Yeah, no, and again, if I'm talking right now and you're taking the test, and I say out loud, hey, you should probably be studying for a half hour every single day, and by probably, let me drop that word, you should be studying every single day for a half an hour minimum.
Yeah, that's all.
Good. Now, if I'm talking to you and you're taking the test and in your head you're like, yep, I haven't done that yet. Again, baby steps. You got to start somewhere because you want to start now and not 3 weeks from now. Please take a baby step today. If it's your first try at anything today, take that step. Please, I beg you. You will thank yourself later. You will improve your score the more you prepare. Yes, Troy.
So do you think like a lot of materials give us over that time, that'll be enough if we seek out our own?
I said this last week. I think what I give you is probably enough to go through the free response. No. Well, here's what I'll say. Probably, but if you need more, I got more. Like that. Let me say it that way too. So if the free response website alone, that's 35 free response questions. That alone should probably have, I can imagine you would spend a minimum of like 10 to 15 hours on that website to cover what it's all got to offer you. Which is roughly 30 days of studying if you're spending about a half hour a day. And we're within 30 days of test. So already right there, you probably have enough. But if you want more, please don't be shy. If you're like, Brosnan, I want another multiple choice test. Great. Give me 5 minutes, let me print one off for you, or let me go to my office and snag one from my file cabinet. Here you go. Or it's Brosnan, I want more free response. I went through all the free response on the website. I want more. I got more. I got more. I got a lot. Again, I have so much testing stuff. I probably have like 15 to 20 tests worth of both sections.
I said I would.
He did say challenge accepted.
Yeah.
Oh. I got one.
One full everything? Really? I didn't think so. That's
I got one question left, and then I'll have one.
All right. Okay, so let me get started back on buffers. Keep talking to me. Please keep talking to me with the test. If you have questions, if you need more stuff, if you just want me to go over some problems, you're like, hey, Brosnan, I got these wrong. Can you explain them? Yes, I can. Please don't be shy. Please let me help you. And again, if you're not in the mode yet of studying on a consistent daily basis, start. Please, please, please start. And I'm not asking for a lot. Again, even if you spend 10 minutes tonight as your first even consideration of studying, you got to start. You have to start. Because you don't want to push it off. because then you're probably not going to pass that test. Again, kind of scary, trying to scare you a smidge maybe, but it's also the truth. That's the other problem with this thing. That is the truth of the situation. You have to. You have to study if you want to do well. There's no other way to say it. All right, let's go back to buffers. We're on 8.8. We had a good chunk of this yet to do. My guess is it'll take me a half hour or so, so I'm hoping we got a mod at the end of the hour here for homework topic 2. Homework topic 2 is 3 problems. It's going to be due tomorrow night. And again, my hope is we'll give you some time today to maybe get started on that or chip away at it a little bit. So anyway, buffers is where we left off last week, Thursday. A buffered solution is a solution that contains a weak acid and its conjugate base at the same time, or a weak base and its conjugate acid at the same time. Basically, a buffer is a solution that can neutralize either acid or base. And the advantage of having a buffer is that it will maintain its pH. Whether I add some acid or some base to a buffered solution, it has the ability to neutralize both or either, which is a useful thing. And like I said last week, buffers are kind of everywhere. Okay? The human body has buffers. Beverages, food products, a lot of things are buffered, meaning they are set up to maintain a specific pH for that specific, whatever it might be. Okay. Anyway, so let's get into some problems. We left off right here, and our goal of this one was to solve for the pH of a buffer for the very first time. Okay. The buffer we're going to look at is 0.5 molar acetic acid and 0.5 molar sodium acetate. Now, acetic acid is a solution of a weak acid. Okay. Sodium acetate is a salt. It's a salt that contains, okay. All right, so boring.
Why does green keep darkening?
There's a sensor over here, and whenever I walk in front of the sensor, it tries to auto adjust the brightness. It's kind of annoying.
Yeah, it is. I just completely got lost.
But it's just ultra bright all the time.
Yeah.
So, oh, yeah.
Well, you can probably adjust the brightness.
There's probably a setting to just shut it off, but I'm not in the mood to make it.
Profile.
So we have a weak acid, and we have a salt that contains the conjugate base. What do you need to make a buffer? Weak acid, conjugate base at the same time. Okay. Acetate, I can't go to the chemical storeroom and grab a bottle of acetate all by itself. That doesn't exist. Okay? Why not? Why? Because it's an ion. So ions don't exist unless they're dissolved in solution. Okay? They need something to stabilize them. Ions are extremely unstable, so I can't have like a solid form of an ion all by itself. It needs something else with it to make it stable. When I dissolve that salt in water, it dissociates, and the water molecules help stabilize it so that it actually can exist as an ion. All right? But in order to introduce that conjugate base into my buffer, I have to do it in the form of a salt. The salt that we chose here is sodium acetate. The sodium is a neutral ion. We don't care about it. It's a spectator. So I have my weak acid. I have a salt that contains my conjugate base. This is a buffer. Okay, that's the criteria we need. Let's solve for the pH of this thing. The way we're going to do that is we're going to set up an ice table. Okay? And we need a reaction. Now, you'll notice that I gave you the Ka of acetic acid. So we're going to use the acid reaction of acetic acid for our ice table. I have H, C2, H3, O2, and this is aqueous. And I'm going to have on the other side, I'm going to dissociate this. To prove that it's an acid, I'm going to get H1 plus. Wow, that got really good. And I'm going to get C2, H3, O2. Have fun on your adventure. So this is the reaction we're going to set up for our ice table. This is for the weak acid dissociating, basically proving that acetic acid is weak. You put it in water, you get H1 plus, you get C2H3O1 minus, that's the conjugate base. Initially, what's my molarity of acetic acid?
25.
My initial molarity of acetic acid is 0.5. What's my initial molarity of H1 plus? What's my initial molarity of acetate? Not 0. This is not just our weak acid. It's our weak acid with some salt. And the molarity of that salt is 0.5. Now, this is a salt solution in water. What do salts do when they dissolve in water? How much? 100%. Salts are strong electrolytes. They dissociate 100%. So if I have 0.5 molar sodium acetate, what I actually have is 0.5 molar sodium, 0.5 molar acetate. Do we care about the sodium? No, it's neutral. We don't care. We care about the acetate? Yeah, we do. Very much so. So this is the difference. That's a product. Okay, this is the difference between this ice table and any other one we've done so far. I've got acid, but I also have conjugate base. I've got both, because that's what a buffer is. Yes, yes.
So like on the AP test, if you a question like this, would it say buffer solution or you just start
They do both ways.
it?
Yeah, I mean, so that's a very good question. The question was, if you didn't hear it on the video, are they going to tell me this is a buffer, or are they just going to give me this stuff and think that I'm going to be able to recognize that it's a buffer? Depends. They do it both ways. Sometimes they'll be blatantly obvious and say, the following buffered solution, blah, blah, blah. And sometimes they'll just give you other things and expect you to recognize that it is such. Anyway, so here's my initial for the ice table. Which way am I going to shift? I have to shift towards the products, don't I?
Yeah.
I've got some reactants, I've got some products, but the problem is this is still 0, right? If I set up Q, which is products over reactants of where we are like right now, Q would be 0, because this product is 0. So in that instance, we only have one choice. We must shift to the right, because there's no such thing as a negative K value. K values are only positive. Okay? So we must shift towards the products. As a result, my change here is going to be minus x plus x plus x. And at equilibrium, I'm going to have 0.5 minus x, x, and 0.5 plus x. Okay? Keep going. Now, the end goal is to solve for the pH of this thing. What do I do now? Let's solve for x. How do I do that? Let's set up Ka. Ka is products over reactants. I have H1 plus multiplied by C2H3 O2, 1 minus, divided by H C2H3 O2, like such. Do we know the value of K? We do. That's good. So I'm going to have 1.8 times 10 to the negative fifth equals products over reactants. My products are x multiplied by 0.5 plus x. And my reactant is x. No, sorry, 0.5 minus x. How's that algebra look? We've got like a 0.5 plus x and a 0.5 minus x. The problem is we're going to get a squared term in the numerator, right? And then we're going to have like quadratic and all that fun stuff. So what do we normally do in this instance? We ignore some of the pluses and minuses, right? Because again, the theory is that this little additional and that little subtraction are really, really, really tiny. I mean, the theory is that this is going to shift such a minuscule amount that we can ignore those values of plus or minus. We're going to do that here as well. Let's ignore them. We're going to ignore two of them.
What?
Because we have a plus x on in the numerator and a minus x in the denominator. So then, what do we get? I get 1.8 times 10 to the negative fifth equals 0.5x over 0.5. And 0.5 over 0.5, of course, is 1. So literally, x equals 1.8 times 10 to the negative fifth. Okay. What did we just solve for? Uh-huh. And what does that equal? H1 plus. How do I solve for pH? I feel like it's very much doing this dipping thing more than it was previously. What do you get for a value of pH? Four point something. 4.7 something.
4.74 or 7.5.
If I took the negative log of Ka, what would that be? Negative log of Ka equals pKa. And I just did the negative log of H1 plus and it equals pH. So pH and pKa would be the same. When does that happen? Halfway point. What's also true at the halfway point? Yeah, that's true. Your weak acid and your conjugate base have the same molarity.
I don't remember that.
You don't remember that one?
I don't.
It's there. What was the molarity of our weak acid and our conjugate base?
Oh, they're the same.
They're the same. This is all related.
Wait, so why is
Because we have a weak acid.
that's like stronger than the base?
Yeah.
Okay.
Yeah. We're gonna dive deeper into this tomorrow. But for now, we've done this correctly. All right. Let me recap. We had a buffer. That buffer contained weak acid and conjugate base. What we did is we set up an ice table for that weak acid, and we entered in our initial values for both. We set up K, we solved for X, and we determined that X is actually equal to our Ka from this problem. As a result, the negative log of that equals pH. Okay? We solve for H1 plus, negative log is always pH. So the buffer of 0.5 molar acetic acid and 0.5 molar sodium acetate equals, the pH of that buffer is 4.745. Try another couple stuff. The buffer in question 3, previous one, contains a weak acid and a weak base. Show the chemical reaction for how the weak acid in the buffer can neutralize strong base. What was the weak acid in our buffer? What was the weak acid in the problem we just finished? There it is. And we're going to react this with strong base. What's the formula for a strong base? OH. Does it matter what the cation is? It doesn't. That's a spectator. So I'm going to add some hydroxide. What's going to happen when I add hydroxide to this weak acid? It's going to neutralize one another, right? This is the acid, that's the base. This will donate, this will accept. And I'm going to get C2H3O2, 1 minus, plus H2O. Okay, this is driving me nuts today. Where's the settings? Auto, no.
There we go.
All the way up, all the way up.
Oh,
Yeah, it's the school's electricity, who cares, right?
yeah.
Wait, why is there a screen behind this? What's that?
So it's not a empty space.
That was a different type of, like, smart board thing they were trying to buy, but the functionality of it just sucked. So then they bought another one. You know,
Yeah, it was in the.
Oh, really?
Yeah.
Nice.
Is it still open?
I don't know.
acres.
Oh,
All right, well, again, I just work here. Number 5, show the chemical reaction of how the weak base in the buffer can neutralize some strong acid. What was the weak base from our buffer? What was the weak base from our buffer in the previous problem? It is acetate, yes. Now, more specifically, I guess you could say it's sodium acetate, but the sodium part doesn't matter. So here's my base, and now I'm going to add strong acid. What's the formula of a strong acid? H1 plus. Does it matter what the anion is? No, it doesn't. It's a spectate. Whether it is HCl, HBr, HI, HNO3, HClO4, doesn't matter. That other ion that's attached to our strong acid is irrelevant. It's just going to be a spectate. So what do we care about? The H1 plus. How are these going to react? Base, acid. This will donate, that'll accept. And we get this. So here's the deal. I said this last week. I'll say it again right now. I've got a buffer. Buffer contains the weak acid and it contains the conjugate base. Both are in my solution. If I add some base, the weak acid will neutralize it in my buffer. If I add some acid, the weak base in my buffer will neutralize that. When I add base, my weak acid neutralizes it and I get, or I produce, more conjugate base. If I add acid, my weak base neutralizes that acid and I produce more weak acid for my buffer. Both of these equations basically just produce more of the opposite piece of our buffer. Okay, let's try some more. If 0.2 moles of sodium hydroxide are added to 1 liter of a 0.7 molar acetic acid solution, would this create a buffer? What's the definition of a buffer? What do we need? What does a buffer contain?
It contains both a weak acid and its conjugate base.
A weak acid and its conjugate base. So I have 0.7 molar weak acid. So far, so good. I've added 0.2 moles of sodium hydroxide.
That's not.
That's not its conjugate base.
That's not.
that's
Oh, wait.
it's a strong base, and that's probably minus close to its conjugate.
Okay, this is aqueous. Sorry, not you, aqueous. Okay. So I have this. I add some of that. I'm going to do like the world's smallest ice table. Or try to. 0.7. Or I suppose this is a mine table. I apologize. 0.2. 0. And who cares? What's going to happen when an acid and a base neutralize one another? They neutralize and neutralize and neutralize until something runs out. What's going to run out? The OH. How much are we going to lose? All of it, right? And then at the end, this is a mind table, by the way, sorry, just kind of smashing it all in here. I'm going to have 0.5 weak acid, 0 strong base, and 0.2 conjugate base. Did I make a buffer? Is this a buffer? It is. That feels very weird, doesn't it? Correct. Their molarities are different, right? I have different moles of each. Correct. Their molarities are different, but do I have a weak acid? Yes, I do. I have 0.5 moles of my HC2H3O2 still left. Do I have its conjugate base? I do. I produced 0.2 moles of it after this neutralization occurred. So I can have a weak acid and neutralize some of it. I don't want to neutralize all of it. If I neutralize all of it, then I've got 0, and then I don't have a buffer anymore, right? But if I neutralize a little bit of my weak acid, what I'm producing is conjugate base. This did make a buffer. You can create a buffer with weak acid and then neutralizing some of it, a portion of it. Okay? If I start with weak acid and neutralize some of it, I produce its conjugate base, and I do have a buffer. Yes? Mine tables are for neutralization, acid, base. Ice tables are for equilibrium, meaning like in this unit, that's like setting up Ka or Kb. So we would have like weak acid dissociating on the product side, or you'd have weak base plus water to produce conjugate acid.
So if they do look at
You use an ice table. Yes.
and then if they don't do
Yeah, I'll say it even a little bit more clear. If they give you an acid and a base, it's a mine table. But if they just give you an acid all by itself, or a base all by itself, that's an ice. And actually, so there's a sheet in the back of your packet called like helpful tips or something like that that I sent out a couple years ago.
Oh, that would have been nice.
That's what I'm telling you. Keep going. Helpful tips on buffers / titration / indicators. There's a bunch of bullet points on that sheet that go over when you use each and why you use each. So, no comment.
If it makes you feel better, Roger, you did mention it at the beginning of the unit.
No way.
I 100%.
It's not my class.
Didn't use it.
Yeah, I could easily.
Oh, yeah. well,
Okay. Scenario B. I have 0.7 moles of sodium hydroxide, and I add that to 0.7 molar acetic acid. Will this create a buffer?
No,
Oh,
because it
man.
both won't be present, so it'll be neutral.
Yeah, well, okay, so I'm not going to write up the whole thing again. But if I use the same mine table, right? What's the difference between A and B? The difference is instead of adding 0.2, I'm adding 0.7. If I add 0.7 of my strong base, what's going to happen? All the weak acid is going to get fully neutralized. So what am I going to be left with?
Just the.
I'm going to have conjugate base and nothing else. Is that a buffer? No, it's not. Okay. Suppose I could answer my own question. Would this create a buffer? Yes. Would this create a buffer? No. Okay. And the reason is all I'm doing is replacing the 0.2 with 0.7. So I would replace okay, and what does that do? That neutralizes the acid 100%. And that's why I do not have a buffer. What do you need to make a buffer? Weak acid and its conjugate at the same time. Or a weak base and its conjugate acid. I need a weak substance and its conjugate at the same time in the same solution. In the first one, we achieved that because I neutralized some of this to create some of its conjugate. So I had both. That's a buffer. In the second one, I've neutralized all of this. So I only have weak base, nothing else. That's not a buffer. I need both. C, what if I add 1 mole of sodium hydroxide? have 0.7 of the weak acid still, but now I'm adding 1 mole of hydroxide. What am I going to be left with?
Yeah.
I'm going to be left with a strong base because I'm going to have excess, right?
Yeah.
I'll write this one out just for the sake of argument, I guess. We're here. Oh, come on. So I have H, C2H3O2 plus OH, 1 minus, yielding C2H3O2, 1 minus, plus water. Okay, I'm not going to deal with the symbols and all that good stuff. This is a mine table. I have 0.7. I have 1.0, 0, and who cares? Okay, what happens? I'm going to lose all of my weak acid, right? And I'm going to be left with 0.3 molar strong base, and I'm going to get 0.7 moles of weak base. Is this a buffer? No, it's not. I don't have weak acid. I've got strong base and conjugate base. That doesn't make a buffer. I need both weak acid and its conjugate at the same time. So moral of the story is this. If I start with weak acid, which we did in all 3 of these, right? If I add a little bit of strong base to neutralize some of it, I'm going to make a buffer. If I start with a weak acid but neutralize all of it, well, then I don't have weak acid to make it, that's not a buffer. And if I go too far and I add way too much strong base, okay, now I have excess, the pH is really going to change drastically. How would I solve for the pH of this solution? I've got weak base and strong base. Which of those do we care about more? Strong. How would I solve for the pH? I would take the negative log of this to get to pOH. 14 minus that would be pH. I have additional weak base, but this is going to influence the pH way more than that will. So really, we only need to acknowledge the strong base in terms of calculating the pH. We did that previously. That was like 8.3 or something. Sorry, go ahead.
So if you're mixing this like a jar,
Uh-huh.
what is it? These are all aqueous, right?
Yep.
So
Water's liquid, but yeah.
yeah, what would that like look like?
It would all, the whole thing would just be colorless.
Yeah, like hypothetically, like so you have the conjugate. Never mind. You have the conjugate base and then
Yep.
there's just strong base also, it's just like hanging around.
No, they wouldn't interact. They're both bases, so they would
Okay.
both just coexist as ions in the solution.
Okay.
What is the resulting pH if 0.01 moles of sodium hydroxide are added to 1 liter of the buffer in problem number 3? We're going to take our buffer now from problem 3, which was acetic acid and sodium acetate, and we're going to add some strong base and see what happens. Let's see how far that pH moves. Okay? Here's the setup. I am adding strong base to my buffer. What's going to happen when I add that strong base to my buffer? What's the buffer going to do? Buffer's going to neutralize it. We got to set up a mine table first. Okay? Set up a mine table first. We have weak acid plus hydroxide, because that's what we're adding. We're adding 0.01 moles of sodium hydroxide. This is aqueous, aqueous. These fully neutralize each other, and what we produce is conjugate base and water. And now let's set up that mine table. How many moles initial did I have of the acetic acid from problem number 3? How many moles initial did I have from problem number 3? Should be 0.5, right? Yes? Okay, well, you're all, yes. How many moles of base am I adding? 0.01. How many moles of acetate did I have in my buffer from problem number 3? I had 0.5, right? I had 0.5 molar acid, 0.5 molar base. Now, in reality, these are moles in a mine table. So technically, this is moles and moles. But they told me I had 1 liter, so that makes life easy. We didn't have to convert anything. In a mine table, you use moles. In an ice table, you use molarity. But we're in 1 liter solution, so this is not an issue with this problem. All right, what happens when acids and bases react? They neutralize and neutralize and neutralize until something's gone. What's going to run out? The OHs. I'm going to use it all. Thanks. What am I doing?
What are you doing?
I don't know. How's that look? Right? Logical? I had acid, I had base, they neutralize one another. What happens? I subtract off however much I neutralized, and then I would add that to the other side. So at this point in time, what I have is weak acid conjugate base. Still a buffer. What's the pH after we've neutralized 0.01 moles of hydroxide? That's the goal. Now, how are we going to set up this and solve for the pH? We need a rice table. Make the color really ugly. Okay. The reaction that we care about is for the weak acid. So I have HC2H3O2 breaking apart. This is a equilibrium reaction, I apologize. Into H1 plus C2H3O2 1 minus. And now in my ice table, I'm trying to solve for the pH, right? What do I have initially for the acid? I have 0.49. What do I have for the H1 plus? Nothing. What do I have for the conjugate base? 0.510. Which way is this going to shift? Has to. I still have 0 for the one product, right? So I'm going to shift right, and as a result, I'm going to subtract some quantity of X. I don't know what that is. And what I'm going to get at the equilibrium then is 0.490 minus X, X, and 0.510 plus X. Yeah, same acid, same Ka. Correct. This is the same acid we had from earlier, so we're still using the same K value. Ka equals products over reactants. Ka still equals 1.8 times 10 to the negative 5. And this is going to equal X multiplied by 0.51 plus X divided by 0.49 minus X. We ignore the plus X and the minus X, because again, the assumption there is that they're really, really tiny. So instead, we end up with 0.51 divided by 0.49. And that's our value of X. Right? You can all solve that. What do we get for a value of X? If I take 0.51 divided by 0.49, that sound right? Yes? Okay, and if I take the negative log of that, I'll get my, I'm sorry, this is my hydrogen ion concentration, right? There it is. So this is 1.7 times 10 to the negative 5. And if I take the negative log of that, what do I get for a value of pH? 4.762. Okay, let me recap this whole thing. Way back at the top of 8.8, the very first thing we did was there was a box that said review. In that problem, we had pure water. The pH of pure water is 7. We added 0.01 moles of hydroxide. And what happened to the pH? The very first problem. After I added 0.01 moles of hydroxide, what happened to the pH of the water? It went from 7 up to what? 12. 7 to 12 with 0.01 moles of hydroxide. When I added 0.01 moles of hydroxide to my buffer, how did the pH change? The pH went from 4.745. I add 0.01 of my base, and what did it end up at? 4.762. So in pure water, I add 0.01 moles of base, and the pH jumps literally 5, from 7 to 12. For my buffer, I add 0.01 moles of strong base, and my pH moved, what is that? 17 thousandths, I'm sorry. Like, not at all. So buffers are doing what they're supposed to be doing. Meaning, we had a buffer with weak acid and conjugate base. We added some strong base to it, and it still resisted that pH change. That's the whole idea behind what these things are about. If I added that same quantity of base to water, the pH changed dramatically. But I added to a buffer, and it hardly moves. Now, it became more basic, right? That makes perfect sense. We added base. So if I started at a pH of 4.745, and I add some base, I should totally expect my new pH to be above 4.745. That feels logical. And we see it. Now, all of this, do you see this whole slide right here? I see it. Tomorrow, I'll give you an equation, and we can do this in like, I don't know, a quarter of the time. We're going to streamline the process of solving for the pH of buffers.
So would the pH have changed a lot more if we had broken the buffer as well?
Oh, yes.
It
So
would have changed a lot, right?
yes, if you break the buffer, then you're basically back to water, right? And it's going to dramatically change.
Yeah, so like if we added 0.51,
Correct.
which would be just, it would seem like just a little bit, like when you look at it like this, but how it would really be, it's like it's water and you're adding
Yes.
It would jump up a bunch.
Yes. If you add 0.51 moles of base to this, you would be at a pH of 12 because you would have an excess of 0.01 moles of base.
I got
But if you keep the buffer system in place, it's going to move just a little bit.
you. Okay.
Cool. Sorry for not giving you much time on your homework, and by much, not much, I imagine you're probably not going to do anything.
Yeah.
Um,
I have a question.
yeah.
It's about
If you're online, you're free to go. I'm going to stop my recording, Jack. Hold on. Isaac, Sarah, have a lovely day if you're still hanging around.